All right, this is going to be the last video of the second week. In this video, I'm going to talk about how to multiply two matrices. So we are discussing how to simplify a system of linear equations into a single equation in terms of matrices, right? So suppose we have this linear equation system, so having two equations and two variables, all right? And using the basic operations we studied in the previous video, we can rewrite this system as, because if we take a look at x1 terms, okay, then we have two terms, 2x1 and x1. So using the scalar multiplication, we can factor out x1. So can rewrite this x1 times matrix 2 and 1. All right. Now taking a look at a x2 and using the scalar multiplication one more time, factoring out x2 times matrix 3 and negative 2. And then the two expressions on the left-hand side is simply the addition of these two matrices. Okay? And on the right-hand side, we have a constant matrix 8 and 0.5. Okay? So using the operations we studied so far, we can simplify this system into this equation. And in fact, it turns out that we can take one more step. So to simplify further into this matrix form. Okay, now it involves multiplication of two matrices. So now we study how to multiply two matrices in this video. Okay, so what's the benefit from this simplification? Now we can use matrix algebra to solve this equation in a more compact way. Okay, so you're going to see how practical this simplification is. So the question we are going to address in this video is, we have two matrices A and B. How do you multiply them? Okay, and just like addition, so we need some conformability condition using our textbook terminologies. So addition is defined only in certain condition, under certain condition. And similarly, the product A times B, but we do not use symbol, this X symbol, is defined under certain condition, certain conformability condition. That is, if we have two matrices A and B, where A is n by n matrix and B is p by q matrix, okay? And for product to be well defined, the number of columns of the first matrix A, that is given by n, and the number of rows of the second matrix B, that is given by p, and these two numbers should be equal to each other. So the product A times B is defined if and only if n equals p. Okay? In such a case, these n and p, these two common numbers are cancelled off, and the dimension of the product, if we call the product AB as C, then the dimension of this matrix C is going to be n by q. Okay? So the number of rows of the product is determined by matrix A. So the matrix A's number of rows is m. That's the same as the number of rows of matrix C. And the number of columns, Q, is determined by the matrix B. All right? So we have a specific example here. So A is given by 1 by 2 matrix. We have 1 row and 2 columns. And B is given by 2 by 3 matrix. We have 2 rows and 3 columns. Okay? So A is 1 by 2. B is 2 by 3. So AB, product A and B, is well defined because the number of columns of the first matrix, that is 2, and number of rows of the second, that is 2 as well. So these two are the same, so AB is well defined. All right, that's the conformability condition for multiplication. Okay, and as a result, A times B is gonna be 1 by 3 matrix. So it has a 1 column and one row and 3 columns. So C is gonna be it takes this form: C1, C2, C3. Okay, that is a row vector. This is typo, not a column vector, because that it has only one row. It has only one row. Okay, but on the other hand, if we think about so if we change the order and think about B times A, and B has dimension 2 by 3, A has dimension 1 by 2. So now, we can compute this product. The 3 is different from 1. All right? So BA is undefined. All right. Then how do we multiply? So now we know how to determine the dimension of the product. Okay? And we studied a conformability condition when product is defined. Now, how do you compute the product? Now, that's the remaining question. All right? But for exact, to compute the product of two matrices, we need one more notion. All right? So we have to know how to multiply two vectors. Okay? In the previous video, I already told you there is some relationship between matrices and vectors. And in fact, matrix can be thought of as array of vectors. So going back to previous example. So here A is given by matrix 2 and 3. All right. What is the difference this matrix and so between this matrix and vector 2, 3? All right, that's the same, right? In the sense that matrix 2 and 3 is different from 3 and 2. And likewise, vector 2, 3 is different from 3, 2. All right? Order matters, right? So, and then, these two expressions have the same elements, okay? So actually the matrix A can be thought of as a one row vector, okay? And matrix B can be thought of as an array of 3 column vectors. So these are 3 column vectors or 2 row vectors. Okay, so you can see some similarity between matrices and vectors. Actually, they do have a very close relationship. Okay, so in order to figure out how we multiply two matrices, we have to figure out how we multiply two vectors. Okay, and you're gonna see our multiplication of two matrices is just simply about a natural extension of multiplication of two vectors. All right. So here is the way to multiply two vectors. So we have two vectors v and u. Okay. So v is given by so it has n elements. So it's an ordered n tuple. So this is so if we define vector in two-dimensional space, say v has only two elements, v1 and v2, that is ordered pair. Okay? And if we define vector v in three-dimensional space, so now it has three elements, that is a ordered triple. Okay? Then if we define vector v in a general n-dimensional space, that it becomes ordered n tuple. Okay, so we have one vector v and another vector u. Okay, so it also has n elements. Okay, then the product, that is called the dot product, that tells us how to multiply two vectors. So the product of these two vectors is defined as this. Okay, so we first multiply the first components of each vector. So we take the first entry of each vector and multiply them. okay? And we take the second element of each vector and multiply them, okay? And then we add them up to the last component, last element of Vn times Un, okay? So if you are familiar with this sigma notation, summation notation, then we can rewrite this in a compact way. Summation of V sub k times U sub k, where k goes from 1 to n. Right? If you're not comfortable with this notation, please tell me at the live lecture this Friday, and I'm going to explain that. And depending on in which space these vectors are defined, this dot product is also called inner product or the scalar product. If you study math further, you're gonna see several different spaces. So the Euclidean space, so we usually study a Euclidean space. That is just a part of the whole mathematical spaces. Several outstanding mathematicians invented several some spaces. So that is amazing. Anyhow, okay. So that's the way to multiply the two vectors. So here's one simple example. In three-dimensional space, we have two vectors v and u. So v is 2, 1, 0, and u is 1, 3, 5. And the dot product is going to be, this is easy. So that is, we first take first elements 2 and 1 and multiply them, and plus 1 times 3 plus 0 times 5. So we have 2 plus 3, that is 5. Okay? And because a v dot u is a summation of v sub k times u sub k, where k goes 1 to n. And if we change the order, so now consider u dot v, then this is going to be summation of u sub k times v sub k, where k goes from 1 to n, right? So that is the same, meaning that for this dot product, commutative law does hold, all right? So even if we change the order, we have the same result. Okay? So now we figured out how to multiply two vectors. Now they're going back to our question, how to multiply two matrices. All right? Let me explain that with two examples. So the first example is what we saw. So A is a 1 by 2 matrix, 2 and 3, and B is a 2 by 3 matrix. All right? Then we know the dimension of the product is 1 by 3. All right? So it has 3 elements. So it has one row vector. It has a 1 row and 3 columns. Okay? So let me write this let me write the entry of this matrix as C sub 1, 1 and C sub 1, 2 and C sub 1, 3. Okay? Remember, for double subscripts, the first subscript denotes the row. Okay? So we have a same one for the first subscript, meaning that we have just one row vector or one row. And then we have for the second subscript, we have 1, 2, 3. That means we have 3 different columns. Okay? And how do we compute the first entry, C sub 1, 1? That's gonna be the dot product of the first row vector of matrix A and the first column vector of matrix B. Okay? So the first row vector of A, that is 2, 3, right? So now we write this matrix into a vector form, okay? The only difference is we use commas for vectors. And for matrices, we do not use commas, okay, between elements, right? And then compute the dot product. So multiply by the first column vector of B, that is 1 and minus 1, So 1 and minus 1. So which is 2 minus 3. That is negative 1. Okay. So here is the picture. We compute the first entry. So we take the first row vector of matrix A and the first column vector of matrix B, and then we multiply component-wise, okay, and add them together. That is the dot product. All right. And for C12, we take the first row vector of matrix A and then do dot product with a second column vector of matrix B. Okay, so that's gonna be 2, 3 dot. Okay, so the second column vector, that is 0, 3, 0, 3. So that is 0 minus, also plus 9, plus 9. So that is 9. Okay, and for the last entry, C sub 1, 3, that's gonna be dot product of the first row vector of matrix A, because matrix A has only one row vector. So 2, 3 dot, and the third column vector of matrix B. So 1, 2. Okay, the last column vector of matrix B. So this is 2 plus 6, so that's going to be 8. All right, so the product is going to be negative 1, 9, and 8. All right, that's the way to compute the product of two matrices. Let me do one more example. So here we have matrix A, that is a 2 by 3 matrix, and matrix B, 3 by 2 matrix. All right. So the number of columns in the first matrix is the same as number of rows in the second matrix. Okay. So the conformability condition is met. Conformability condition for multiplication is met. So the product AB is well defined. Okay. And then the dimension of the product is going to be 2 by 2 matrix. Okay, so it's going to be 2 by 2 matrix. So it takes this form, C sub 1, 1, and C sub 1, 2, and C sub 2, 1, and C sub 2, 2. Okay? It's going to be scalar matrix. All right. Then how do you compute C sub 1, 1? Now you can see some pattern. C sub 1, 1 is a dot product of the first row vector of matrix A and the first column vector of matrix B. Okay, so that is 2, 1, 5, the first row vector of matrix A, and we take this to compute a dot product with a first column vector of matrix B, that is a 3, minus 1, 2. So 6 minus 1 plus 10, which is 15. And then C sub 1, 2 is a dot product of the first column first row vector of matrix A and the second column vector of matrix B. Okay, so C sub 1, 2, the first and second entry of the product is going to be dot product of the first row vector of matrix A and the second column vector of matrix B. Okay, now you can see some pattern. So A sub 1 is 2, 1, 5. And B super 2, there's a second column vector. So we have to take this as second column. So 4, 2, 1. So now we compute the dot product between these two vectors. So 8 plus 2 plus 5, which is 15. Okay, let me do just one more. C sub 2, 1. All right, now that's going to be A sub 2 and dot B super 1. Okay, so now we take the second row vector of the matrix A, 1, 3, 2, dot, and we take the first column vector of matrix B, 3, or negative 1, 2. So 3 minus 3 plus 4. So that's going to be 4. Okay. I will leave C sub 2 for exercise, but we determined these 3 elements. So that's going to be 15 and 15, and this is 4. Okay. And C sub 2 is the dot product of A sub 2 and B super 2. Okay, so you can compute this. All right, so here is a general formula for matrix multiplication. In general, if we have a matrix A, n by n matrix, and matrix B, n by p matrix, then the product is well defined, and matrix C is going to be n by p matrix. Okay, and its ij entry, so the entry in the ith row and the jth column is going to be dot product of ith row vector of matrix A and the jth column vector of matrix B. Okay, so ith row vector of matrix A is going to be this row vector. So A sub I1, A sub I2, because in matrix A there are n columns, so it goes all the way to A sub in. Okay, and B super J, so the jth column vector of matrix B. Okay, and that is a column vector B1J and B2J, and it goes to B sub nj, because there are n rows in matrix B. Okay, so that is going to C sub ij is dot product of these two vectors. So using summation notation, we can write this as summation of A sub ik times B sub kj, where k goes from 1 to j, 1 to n. All right. So each entry can be computed as the dot product of some row vector of matrix A and some column vector of matrix B. Okay, so the matrix multiplication is indeed some extension of multiplication of vectors. All right, so we can easily figure out some laws of multiplication. So matrix multiplication is not commutative. If we change the order, then we end up with different outcomes. So AB is not equal to BA. Okay, we have seen one example before. AB was well defined, but BA may not be defined, right? But even if both products are well defined, still we may have two different products. Okay, so here is one example. If we have A, this 2 by 2 matrix, and B, this 2 by 2 matrix as well, so 2 by 2 and 2 by 2, so A times B and B times A are well defined. Okay, but their products are different. Those two products are different. Okay, because for AB, let's think about the first entry, or the entry in the first row and first column. That's going to be the dot product of the first row vector of A and the first column vector of matrix B. That is 12. Okay, but think about BA. The first entry of BA right? The very first entry, so at the northwest corner, all right? That's going to be now the dot product of first row vector of matrix B and the first column vector of matrix A, which is -3. All right, so they are different. And so even though two products are well defined, we may have different outcomes. So in general, the commutative law does not hold. But surprisingly, associative law holds. So regardless of which pair we take and multiply, we have the same outcome. So if we first take AB and then multiply them first, and then multiply by C, that's the same as if we take BC first and multiply them and then multiply by A. Okay, that's the same. All right, that is a not straightforward. So there is a nice way to prove this. So, but I think that is beyond our scope. So I'm gonna make some additional note for this proof. And if you're interested, you can just take a look at the proof. All right, but it's not on. It will not be on the exam. And then the matrix multiplication is distributive, meaning that if we have a multiplication of matrix A and a B plus C, then we can distribute A. Okay, so the result becomes AB plus AC. All right, but be careful. We multiply A in the front. Okay, so now A comes in front, meaning that A times B is a AB, not BA, and A times C should be AC, not CA. Right? We can't change the order because commutative law does not hold. All right. Similarly, if we multiply A later, okay, then how to distribute A? That's going to be not AB but BA. Okay, because we multiply A in the second, right? And then C times A is not AC but CA. All right. So we should be careful about the order when we consider multiplication of two matrices. So finally, we have one exercise here. So that is a proof question. So prove that A plus B times C plus D is this expression. All right. And this is just a repeated application of distributive law. So how do you prove this? So we have A plus B times C plus D. And let me call that, so let me define matrix E as a C plus D, okay? And this is A plus B times E, okay? And now using the distributive law, I can distribute E to have A times E plus B times E. Okay, now as A or E is C plus D, so I can substitute back into E to have this. Now apply the distributive law one more time to each term. So AC plus AD and BC plus BD. Okay, so we have the same expression here and here. Here, okay. So we prove the statement. All right. So now you can easily see that was the first leading example, how to simplify a system of linear equations into matrix equation. Now you can easily see this is the same as the multiplication of these two vectors. All right. So such a system linear, this is a summary of the second week. So such a system of linear equations is applied to general equivalent analysis. So when we consider two markets or three markets at the same time, we come up with system of linear equations, and linear algebra and linear equations is so linear algebra is a main tool for the analysis of general equilibrium and others in economics. So say econometrics and optimization theory, all right? So in the second week, we studied elementary matrix algebra. So we defined the matrix and compared with vectors. And we studied how to add two matrices, subtract, and multiply. Okay. And then from in the next week, we go into matrix algebra further. All right. So this is the end of the second week. I think my videos are, so the total videos may exceed 2 hours, but I didn't do enough in the first week. Hope you guys understand that. All right. So see you guys on Friday at the live lecture. You guys have a nice week. Thanks for watching.